So now let's substitute this contour-integral representation of our Bessel function into our sum. And we see that both of the integral and the sum converge. And with some frivolity, we interchange the summation and the integration sign. So let's see what it's going to bring us. Well, first of all, we write down the initial integral. And then the sum. Obviously, everyone recognizes the so-called geometrical sequence sum. Well, actually, there are two geometrical sequences here. The first one is taken from n equals 0 to plus infinity, and the second one from minus infinity to -1. And the interesting thing about these sums, that they have slightly different conditions for convergence. As you know, the geometrical sequence has the radius of convergence of 1. So x, the modulus of x, should be smaller than 1. So for positive n, we have the convergence condition. The modulus of this general term is smaller than 1, which immediately gives you the condition on t. The modulus of t should be greater than 1. For negative n, you can interchange n to minus n, and in the same fashion, you get the opposite condition. So, and now here comes the central idea. You interpret this sum as and the initial integral in two ways. For positive n, you interpret this integral as an integral taking along some contour with radius around, for example, some circle with radius greater than 1. But for negative n, you interpret the same contour as around, again, the contour along some circle, but with radius smaller than 1. So basically now we have two integrals which are almost identical. But the first one is taken along the large circle, and the second one along the small circle. And in the same manner, we understand these sums. The first sum in the first integral is taken along with t greater than 1. It's convergent, and here's the result. The second sum is understood in a sense that the corresponding t's are smaller than 1, so it's again convergent. So let's write down the answers for both of the sums. So here is the first answer. It's simply 1 over 1 minus x. Our x, in our case, is, okay, let's write it down like it's t minus e to I theta minus I pi by 2 divided by t. And the second sum, well, actually, let's change n to minus n. So n runs from 1 again to plus infinity. But this time, the general term is t times e to minus I theta plus I pi by 2. And the result is t times e to minus I theta plus I pi by 2 divided by 1 minus t multiplied by the correct exponential. Now, if you look at these two terms, you will immediately notice that the only difference between them is the sign, general sign. Otherwise, they're completely identical. Indeed, we can multiply the denominator in the second expression by the corresponding exponential to get just identical expression. So now we understand why we got 0 when we try to employ this expression for the asymptotics of our functions. Because if we discard the subtlety of contour integration, so because there should be different contours for each type of sum, then of course we get identical zeros. But now we understand that those are two almost identical integrals, and the only difference between them is the sign. So we can understand, we can interpret the total expression as the integral taking along their largest circle minus the integral taking along the smallest circle. Or we can change this minus sign to plus, but understand that, so this is the unit circle. And we understand the first integral, the integral is taking in their counterclockwise direction along the circle which is slightly larger than the unit circle. And the second integral is taking in the clockwise direction along their smaller circle. Now let's pay attention to the structure of our integrand after we summed it up. Obviously it has a pole, a simple pole at point e to I theta minus I pi by 2, which is some point on a unit circle. And now we see what the crucial difference between these two contours. The first contour goes slightly above this pole. To accentuate this, I actually write here, I draw here a small semicircle, so you can see that it indeed goes slightly above this pole. The second contour, however, it passes slightly below this pole. And of course, the tempting thing is try to shrink the outer contour so it coincides with the inner contour. And since the expression, the integrand, is identical for both integrals, they will cancel each other. So the integral cancel each other with almost everywhere, with the only exception of this small semicircle here and here. So now we see that the whole expression, this whole sum, is reduced to the closed contour integral, but around this pole, around simple pole at point t equals to e to I theta minus I pi by 2. And of course, we know how to integrate integrals around a simple pole. We just use the corresponding Cauchy theorem. And the integral is reduced to 2 pi I times the residue of the integrand. And the residue of the integrand is trivial. We just plug in this value of t into our exponent of the defining the Bessel function. And naturally, in this case, t minus 1 over t is precisely the correct sign, in our case, sign factor. So it's 2i sine of theta minus pi by 2. And using simple trigonometry, we turn it into minus cosine of theta times kr, precisely the plane wave expression. So this is how this idea of the inverse decomposition works for this scattering event without actually any scattering center. And let's see how it's modified in the presence of the magnetic flux.